This tutorial deals with dilations. Previously we've looked at dilations in the form of either multiplying the function by a dilation, so a by f n of x, or actually multiplying the x value by a dilation. We've dealt more with this capital A out the front, so for instance 2x squared would be a dilation factor of 2 from the x-axis. We're actually now looking at this n value as well, which makes life a little bit more complex, but the method we're about to go through should, I suppose, clear that up. We are going to again use this notation of the image and the pre-image, or the coordinate points, so x, y, where if we have a dilation from the x-axis, remember from the x-axis stretches up and down, which means that you're looking at the y value getting multiplied by that dilation, or from the y-axis is multiplying the x value or the pre-image. So we're going to look at the four cases that we have. So 2 from the x-axis. Note 2 is a number greater than 1, so we're dealing with a stretch out. So we're going to go away from the x-axis, which then multiplies our y value by that dilation, so 2y. If the dilation factor is 1/2 from the x-axis, 1/2 is between -1 and 1. So fraction, which means that we squish down, we go closer to the x-axis. Again, dilation factor of 1/2 from the x-axis means we multiply the y value by the dilation. If we do the same sort of thing but from the y-axis, so 2 from the y-axis, 2 being greater than 1, stretches it away from the y-axis, which means the x value gets affected and we multiply that by our dilation factor. 1/2 from the y-axis means you go closer to the y-axis, half a factor closer to the y-axis, and then you multiply that, or the x value, by that dilation factor of 1/2. So that's graphically what we're doing. This is our notation for our coordinate points, and that's what we're going to use when we go and do this algebraically. So the algebraic method. This function is a square root function, y equals root x, and we're saying it's getting dilated by a factor of 2. And I'm missing some little notation here, but it's 2 from the x-axis, so note we're going from here up to 2, so 1, 1 moves to 2, 1, 2. So our y value is getting multiplied by 2. Which means that as far as our coordinate point notation goes, we go from x, y, and we change this to x, 2y, where we have this dilation factor of 2 from the x-axis, which means the y value gets affected. We can do our x new and y new just like normal, so x new is equal to x, because nothing's changed here, and y new, so a new y, is equal to 2y. We're going to rearrange this again, nothing changes here, but y is going to be equal to y new divided by 2, just a rearrangement of this. If we take the x value and the y value and substitute it into our original formula, y equals root x, we get out y new divided by 2 is equal to root x new, technically. Rearranging this, because we never have something with y, we get y is equal to 2 root x. This is a dilation factor of 2 from the x-axis, which is exactly what we've got here. So this method of coordinate points, then rearrangement, and then resubstituting will work, regardless of whether or not it's translations, dilations, or indeed next lesson reflections. Alright, example 1, determine the rule of the image when the graph of y equals 1 on x squared is dilated by a factor of 4. First thing to note here is that the image is what basically the equation is. So we're asking for the equation here. So what we can do is, well, this splits into two questions. So from the x-axis. From the x-axis means that your y value is multiplied by the dilation factor. So our original coordinate point of xy goes to x 4y. So the dilation is in here. Okay, so dilation from the x-axis of 4 means that your y value is multiplied by 4. That gives your new x and your new y. Now making our two equations, x new equals x and y new equals 4y, we do need to rearrange this to get y equals. So we're going to substitute in x equals and y equals to our original equation, but in order to do that, we do need to rearrange this. So we get out y is equal to y new on 4, or 1/4 y new. Now taking our original equation, y equals 1 on x squared, we're going to replace the y with 1/4 y new and the x with just x new. Rearranging this, because again, we never put y with something else, we're going to multiply both sides by that 4, which puts it onto the top. So our actual equation is now 4 divided by x new squared. Alright, so this is from the x-axis, which multiplies the y value. The next part of the question goes from the y-axis. Now if it's stretching from the y-axis, it's a horizontal stretch, which means the x values are affected. So our coordinate point goes to 4xy, so the x value gets multiplied by the dilation factor. This gives us a new x and a new y. Alright, two equations, x new equals 4x and y new equals y. Rearrange that first one to get the quarter x new. Substituting this into our original equation, we get y new on, or 1 on 1/4 x new squared. Now that is a really nasty answer. We would not leave it like that. What we have there is a fraction on, well, a fraction in a fraction, which is just not nice. So what we're going to do is we're going to take this denominator of 1/4 x new all squared and split it into two separate equations, or two separate terms, let's say. So 1/4 squared and x new squared. When we do this, so 1/4 squared is the same as 1/16, and if you keep flip change, you'll get 16 on x new all squared. That's your end answer for a dilation factor of 4 from the y-axis. So this method of coordinate points and doing your alterations for your coordinate points works again for dilations.